Okay. Thank you very much, Susanna, for this very interesting talk. Now we have some time. Now we have some time for questions or comments from the audience. Yes, of course. Yeah.
Because I think this is some outlier of this. We are all in projects, but here we have the project and the maintenance. And the additive manufacturing is a toy that we must use in all the transverse sectors of the industry. And when we say about the advantage of these technologies, we cannot forget the maintenance, because maintenance have to have supplants, spare parts to immediately. And when we are, as was in COVID, many supplies that didn't function. And we have to have the ships, military or not, in the sea, cars in the roads, flies, and everything. So if the supplies don't function, the maintenance cannot repair some equipments like the pump and other things. So, of course, we are here studying the effects of temperature, of fatigue. We are in the beginning, but we want to put in the maintenance for components that are function, and testing in service. We have a lot of things to do before. And the certification for military, for Navy, for aeroplanes, need many tests. So, and we need a lot of, we are thinking in the artificial intelligence, and we don't have database enough to do that. We are in the beginning. This is my comments to this presentation.
Thank you, Teresa. Susanna, I have just a curiosity. If you are interested to investigate the effect of corrosion on
also. Yes.
I think it's very important.
It's not my specialty.
Okay.
More maintenance,
okay.
But I'm interested on the spare part production. Like Professor Teresa said, she has a very good example of pastry paper that we had on Portugal, that the supply chain was broken in some times, and they have to do something to have the components to the industry still working, and so the 3D printers was it. Okay. Corrosion is very important on sea, because a lot near the sea.
Of course.
But like I remember when I was young, once I was with this age, more or less, I was on the sea, responsible of mechanical, and we always have the fire pumping that some, not really on a small piece outside because of the vibration, it always cracks. And then we had 3 on board, but we have to wait to go to on, because they don't have that autonomy on board, and go to a workshop, land, and then work for the opportunities to do that. And that is a small piece that we can print nowadays without really damage.
Okay. Oh, you're welcome. Thank you very much, Susanna. Thank you once again. And so we can move to the next speaker. She is Saveria Spiller, and she will talk about the influence of the process parameters on laser beam welding of additive manufacturing IN625.
Thank you very much. So good afternoon. Thank you for being here at this time. So my name is Saveria Spiller, and I'm working at the University of Padua. And the title of my presentation for today is influence of the process parameters on laser beam welding of laser powder bed fusion in IN625. This is actually part of a broader project about the weldability of nickel-based superalloys. Okay, so some context and motivation of the project. You might know nickel-based superalloys are very appreciated for their excellent mechanical properties, okay, especially in extreme working conditions, especially in high temperature and high pressure. So for this reason, they are often chosen for critical components. Typical examples, gas turbines or gas engine for the aerospace industry and similar. But these components, as you might imagine, they end up to be quite expensive easily for several reasons, for their application, for their complexity, and also for the material, because nickel is one of the most expensive metals. And also sometimes nickel-based superalloys are difficult to machine because of their properties. So in this context, you see how additive manufacturing can actually offer an attractive alternative in the fabrication of these components. We know additive has many advantages and many disadvantages, but still it is suitable for complex designs and small production series, and also it enables to prevent material waste. So what do we do if one of these components get damaged? Repairing is preferable than replacing, but many repairing strategies are based on welding processes. And here another issue comes into play, which is the weldability of nickel-based superalloys. That also depends on many factors, chemical composition mainly, but also microstructure and welding process parameters. Thus, the interest of this project is to study an alternative welding process, which is laser beam welding. It is an high energy density process, and for its peculiarity, it might help in preventing the occurrence of welding defects during or after welding. So as I said, we work on IN625 in this project. This is one of the easier to weld nickel-based superalloys because it's a solid solution strength alloy. And in this case, we work with these 3 plates produced by laser powder bed fusion, which is a well-established process. I assume you are already familiar with the process. You can see the main process parameters in the table. And the 3 plates that we use were printed in 3 different building orientation: vertical, horizontal, and diagonal, with a 45 degrees inclination, which is the threshold to avoid support materials. On each of these plates, 4 different BOPs, bits on plates, were welded using laser beam welding. So how were the process parameters chosen? 4 different combinations of parameters were defined with 2 factors, laser power and welding speed, and a 3rd factor, which is the powder modulation. And for each factor, 2 levels were chosen. So for the sake of simplicity, we can say a maximum and a minimum value. In a nutshell, combination 1, the first combination has maximum power, maximum speed, and modulated power. Combination 2, minimum power, minimum speed, and modulation. Combination 3 and 4 are in continuous mode, which means constant power. Maximum power, minimum speed for combination 3, and minimum power, maximum speed for combination 4. So we have 4 combinations of parameters, 3 plates, 3 building orientation. This gives us 12 different cases to study. Something important to mention, why it's important also to consider the building orientation, because laser powder bed fusion and other processes induces anisotropy at a microscopic level in the components. Here you can see EBSD analysis that were performed on the cross sections of the plates, far enough from the BOPs to avoid any effect of the welding process. And you see in the horizontal plate, we have columnar grains, elongated grains drawing along the building orientation, quite long, while in the vertical plate, we have a more homogeneous distribution, and most of the grains are color-coded with red, corresponding to the 001 orientation. And then the diagonal plate has a situation which is halfway, the horizontal and the vertical plate. So the 12 cases, our 12 possibilities are here represented in this matrix. So the columns are for the columns are for the combinations of process parameters, and the rows are for the building orientation. What is important to say is that the joints that we observed, all the regions that we observed, also with microscopes, are of good quality. So limited amount of porosity, some rare liquated grain boundary, but no solidification cracks and no massive defects due to the welding process. So this was the important first result. Here we are comparing the fusion zone extension because sometimes, often, this is an indicator that it's used to compare and make comparison between joints. So if we transform this matrix in a bar plot, we can see if there are some trends that relates the fusion zone extension to the parameters that were adopted. And here you can see there is a trend related to the process parameters, but specifically to the welding speed. Actually, laser power and power modulation doesn't give a great contribution, not as much as the welding speed. And as you see, the lower is the welding speed, the larger is the fusion zone extension. To restrict the field of investigation, we decided to study all the BOPs in group 1 and in group 3. So the main difference is the welding speed. Performing EBSD analysis on the cross-section of the fusion zone. And interestingly, the structure of the fusion zone is the same. It doesn't depend neither on the building orientation nor on the welding parameters. So we have these elongated grains growing from the boundaries of the fusion zone towards the middle of it. But for example, you might know that when the welding speed is too slow, you might have the formation of equiax grains in the middle of the fusion zone, but we don't see it. So it means that within this range of process parameters investigated, we don't induce strong differences in the fusion zone microstructure, and not even on the microhardness. These are plots comparing microhardness profiles taken from the middle of the cross-sections of all the BOPs of group 1 and group 3. So again, the main difference is the welding speed. And again, the trend, the profile doesn't change, is not affected by the building orientation, and it's not affected by the welding processes. The average of the parent material is 320 HVE points, which is higher than wrought material because of the fine microstructure. And we have a drop in the corresponding to the fusion zone, and this is mostly related to the change in the grain size. Some final considerations about the possible presence of secondary phases. Here we have a micrograph of the dendritic structure inside the fusion zone. And as you might see, first of all, you can see some pores, circular pores, that are probably related to trapped gas because of their morphology. And then you see there are some shiny particles in the interdendritic areas. These are claimed to be, in the literature, Laves phases or MC carbides, mainly niobium carbides, considering the alloy. And indeed, EDS analysis, scan line, we could see that in the interdendritic area, we have depletion of nickel and chromium and richness of molybdenum and niobium. So we decided to investigate deeper these phases with a TEM investigation. As you can see in this schematic, the samples were taken from the horizontal plate from the top surface, including also the fusion zone of the first BOP. So we have two samples, one from the parent material and one from the fusion zone. In the parent material, we found the typical cellular structure. It's typical of additive manufacturing components observed from this observation. But this structure is completely removed in the fusion zone because the welding process reset completely the microstructure. But indexing diffraction patterns, we realized that only gamma phase is present, so we don't have any great precipitation of secondary phases, except for some particles, but they were quite rare. So these dark globes in the parent material and these lighter grains in the fusion zone. These are rich of niobium, but too small to get a precise indexing of the diffraction patterns, so we couldn't identify them yet. So to conclude, the first important thing is that the weldability of IN625 is preserved, even if the fabrication process is additive manufacturing. The building orientation hasn't got a significant effect on the tests performed, and not even the process parameters, with the exception of the welding speed on the fusion zone extension. But we have to remember, considering only these tests and considering the ranges investigated. And finally, we also could find a limited amount of precipitation of secondary phases in the fusion zone, and this is important to know because these phases, these intermetallics, are detrimental for the integrity of the joint. They increase the fragility, they might be a problem for the weldability, so this is also a good news. And that was it from my part. Thank you for the attention.